Alright guys, today we're going to be looking at our double angles formulas from the back of our identities page. So if you take out that identities page you guys have been using, we're actually going to be starting with the back now, that top section, which is about our double angles. So the first thing we're going to look at is just where these equations and where these formulas come from. In order to show where they come from, we're going to look at the sine of 2x first. And if you realize the sine of 2x is the same thing as the sine of x plus x. And the sine of x plus x we can expand using our sum and difference properties. So the sine of x plus x, if I plug that into our sine a plus b, that becomes sine x cosine x plus sine x cosine x. And let me go ahead and actually rearrange those the order it is in your chart. On your chart it would be cosine a sine b in that order. But since they're both an x, and because we're multiplying, you can multiply in any order, I could rearrange it if I wanted to. And because I could arrange that, those actually are the same term. And those two terms can combine into 2 sine x cosine x. Alright, so again, if we look at the cosine of 2x formula, I can do something very similar. So the cosine of 2x is the same thing as the cosine of x plus x. So again, I'm going to expand that using my sum and difference formula. So that can expand into the cosine of x times the cosine of x, because it's cosine A, cosine B, minus sine A, sine B. Now if I simplify this, that gives me a cosine squared minus sine squared. And that is not equal to 1, because if you guys remember, our Pythagorean identities were sine squared plus cosine squared equaled 1. However, I can use those Pythagorean identities to rewrite this a few different ways. Because if you look at your formula chart, there's actually 3 different options here. And those just come from rearranging some things based on those Pythagorean identities. So if I take this Pythagorean identity and I rework this, if I want, I could rearrange this and I can get my cosine squared by itself. If I did that, cosine squared would equal 1 minus sine squared. So I can replace cosine squared with 1 minus sine squared. And then if I combine my like terms, I get 1 minus 2 sine squared x. And then finally, my third one here would come again from rearranging that same function, but instead of getting cosine squared by itself, I'm going to get sine squared by itself. And if I were to rearrange my original Pythagorean identity, it would be 1 minus cosine squared. So I could rearrange this one and make it cosine squared minus, and remember I'm subtracting that entire quantity, so I'm going to put it in parentheses. And that's going to affect my sign here. Whoops. And that should be minus cosine squared there. So if I distribute that, I'm subtracting both of these, so it's minus 1, it's actually going to end up being plus cosine squared. So when I combine that, I get 2 cosine squared minus 1, and that's the third identity on my paper. So all 3 of those 3 final ones there, those are all listed as cosine of 2x, and any of those 3 can be used at any time. Alright, so the last thing we're going to look at is this tangent of 2x. So the formula written here is what's written on your chart, but what I also want you guys to remember is anytime you have tangent, tangent is equivalent to sine over cosine. So as long as that argument is the same, you can always use tangent as sine over cosine, and sometimes that's going to be a little bit simpler for us. Alright, so now what we're going to do is we're just going to look at a couple of applications of these double angle formulas, and they're going to be very similar to the sum and difference properties that we used. So this very first one, it tells me that the sine of x is 3/4, and then it tells me that that x is in between pi over 2 and pi. So I'm going to draw a picture for this because it's going to help me out. Pi in between pi over 2 and pi is the second quadrant. So I know x is in the second quadrant. So my opposite is 3, my hypotenuse is 4. If I do the Pythagorean theorem, my missing side is the square root of 7. But because of where it's located, that needs to be a negative square root of 7. So now what we're going to do is we're going to use our formulas to actually find what this is. Remember, x itself is not 3/4. The sine of x is 3/4. So we're going to expand this using our chart, and then we're just going to start filling in values that we know. So I know I still have a 2. The sine of x can be replaced with 3/4, And now the cosine of x I can replace by looking at my chart, or looking at my triangle. Cosine is adjacent over hypotenuse. So I'm going to replace cosine of x with negative root 7 over 4. And it's not just replacing x, it's replacing the entire cosine of x. And now at this point I'm just doing some math with these fractions. Remember 2 is actually 2 over 1. And I multiply straight across the top and across the bottom, and I reduce to get my final answer. And we're going to do the same thing with cosine. But with cosine, there are actually a couple different options I could use. I'm going to get the same answer no matter which one I choose, but I'm just going to go ahead and do the first one on here because I've already found both my sine and cosine. So I've got cosine squared x minus sine squared x. So the cosine of x we already found. That was a negative square root of 7 divided by 4. And that value will be squared. Sine of x I already knew as well. That was given. That's 3/4. And that's also going to be squared. And just remember, whenever you square your fractions, you square the top number and the bottom number. So this left fraction becomes 7 over 16. My right fraction becomes 9 over 16. I already have a common denominator. So I get a negative 2 over 16, which reduces to a final answer of negative 1 over 8. And then finally, my last one on here is the tangent of 2x. And if I want, I can go ahead and use that formula and I can plug in my tangent values, which would be the opposite over adjacent of my triangle. Or, since I've already found my sine and cosine, I can just remember that this is the sine of 2x divided by the cosine of 2x. So that means my tangent value would be negative 3 root 7 over 8 divided by negative 1 over 8. But remember, when we divide fractions, we actually are multiplying by the reciprocal. And what's going to happen here after I reduce, I'm going to end up with just a positive 3 square root of 7. Alright, now there is one more application we're going to look at that, again, we also already looked at with sum and difference. We did this on day 3 of our sum and difference properties. And these are my general solutions and solving equations for specific values. So if you look, we're going to start with the general solution. The equation I'm given for sine x cosine x is very similar to one of the problems that I have. However, it is slightly different because the problem that I have is actually 2 sine x cosine x. But I can very easily make this left side have a 2 in the front simply by dividing by 2 because that is just one term. And since this is an equation and not a proof, it's okay to go ahead and work from both sides. So now my left side looks like my double angle property, so I can rewrite that as the sine of 2x. And now the only way to get this argument by itself, the only way to get 2x by itself, is to rewrite this function as an inverse. So I'm going to rewrite this as sine inverse of 1, and that's going to equal the entire argument. So now I need to find all the places where sine could be 1, and if you remember, that's going to be one of your border lines. And the only place between 0 and 2 pi that I'm going to have a sine value of 1 is at pi over 2. So that is the only place within one full rotation of the unit circle that I would find a sine value of 1. But to find my general solution, remember, I had to put plus 2 pi n because that would find all the coterminal angles as well, and that's still equal to 2x. So now, what I have to do to get x by itself is divide by 2, or multiply by 1/2, and remember, that has to be every term. So now, I'm going to get pi over 4 plus pi times n as my general solution. So that's part A, that's my general solution. And the last part, I'm going to use my general solution to find all of the values that are in between 0 and 2 pi. So if I look, the very first value I'm given is pi over 4, and that falls in that range. So if I subtract 1 pi with a common denominator that's 4 pi over 4, that would be a negative 3 pi over 4. And I don't know what I'm writing here. And negative 3 pi over 4 does not fall in that range. So that's one I'm not going to use. So then I would take that same starting number, and I'm going to add that interval. So I'm going to add 4 pi over 4. So now I get 5 pi over 4, and that does fall in that range. If I were to add 4 pi over 4 again, I would get 9 pi over 4, but 9 pi over 4 is going to be outside of that 2 pi range. So these are the only two values that fall between 0 and 2 pi.